If you've ever tried working with a microcontroller, chances are the first thing you did was connect an LED. You write a few lines of code, upload it, and nothing happens. The LED just sits there like it's ignoring you. Most of the time, the problem isn't your code. It's that digital input and output are misunderstood. Once you really understand how these pins work, suddenly a lot of embedded systems starts making sense. Digital input and output is basically how your microcontroller interacts with the real world. When you read a button, that's a digital input. When you turn on an LED, that's a digital output. Sounds simple, right? But behind that simple idea, there's actually a lot going on inside the chip. And if you don't understand it, you'll run into weird bugs. LEDs flickering randomly, buttons that seem to press themselves, sensors that give garbage readings. Let's start with digital outputs. When a microcontroller pin is configured as an output, it means the chip is actively driving that pin either high or low. Think of it like a light switch in your house. When it's high, the pin pushes voltage out. When it's low, it pulls the voltage down to ground. Inside the microcontroller, there's actually a small transistor circuit doing this job. Most datasheets show this as something called a push-pull output driver. One transistor pushes the voltage up to VCC. Another pulls it down to ground. That's how the pin can quickly switch between high and low. Now let's talk about digital inputs. An input pin works differently. Instead of pushing voltage out, it just watches what voltage is present on the pin. If the voltage is high enough, the microcontroller reads it as a 1. If it's low enough, it reads it as a 0. But here's something beginners often don't realize. If nothing is connected to an input pin, it can float. And when a pin floats, the microcontroller starts reading random highs and lows. That's why pull-up or pull-down resistors exist. They give the pin a default state so it doesn't behave unpredictably. If you open a microcontroller datasheet, you'll often see parameters like VOH and VOL. VOH means the voltage level when the pin outputs a high. VOL is the voltage level when it outputs low. These numbers tell you what the real electrical behavior of the pin is, not just the logic level your code sees. Here's where real engineering experience kicks in. Not all pins can drive the same amount of current. Some pins are safe for LEDs, others aren't. Some pins have internal pull-ups, some don't. And if you try to power something like a motor directly from a GPIO pin, you might damage the microcontroller. That's why embedded engineers constantly check the datasheet before connecting hardware. Imagine you're building a simple door sensor. You have a magnetic switch connected to a microcontroller. When the door opens, the switch changes state. The microcontroller reads that input and triggers an alarm. At the same time, it might activate an LED or a buzzer using an output pin. That's digital input and output working together to create a real system. A few mistakes show up again and again when people start learning embedded systems. One is forgetting pull-up resistors, which causes floating inputs. Another is connecting LEDs without current-limiting resistors. And another one is assuming a GPIO pin can power anything. Remember, GPIO pins are meant to control signals, not power heavy loads. So let's summarize everything quickly. Digital outputs drive voltage out of the microcontroller. Digital inputs read voltage coming into the microcontroller. Pull-up and pull-down resistors keep inputs stable. And the datasheet tells you the electrical limits of every pin. Digital input and output might seem simple at first, but it's actually the foundation of almost everything you'll build in embedded systems. Once you really understand it, working with sensors, displays, and communication protocols becomes much easier. If you enjoyed this kind of practical breakdown, consider subscribing and liking the video. And as always, keep building.